Our journey through the cosmos often reveals astonishing truths about our own world. We look up at the stars, not just for wonder, but for answers. For Japan, an island nation with a thirst for energy, one of those answers might be orbiting high above us right now. In 2025, Japan launched a groundbreaking mission named Ohisama, which beautifully translates to sun. This isn't just another satellite, it's a bold first step in a quest that sounds like it was pulled from the pages of science fiction. The goal is to capture the sun's relentless energy in space and beam it down to us here on Earth, providing a clean, limitless source of power. The Ohisama satellite is a pioneer, a small but mighty explorer testing a grand idea. It's not meant to power a city, not yet. Its initial mission is more modest but profoundly important to prove the concept works. Weighing around 180 to 400 pounds, it orbits our planet at an altitude of about 400 kilometers, racing through the void at over 17,000 miles per hour. Its purpose is singular and elegant. It will unfurl its solar panel, soak up the unfiltered sunlight, and perform a kind of technological alchemy, turning light into a focused beam of energy aimed at a specific target on the ground. This experiment is a test of precision on an astronomical scale. Imagine trying to hit a target smaller than a postage stamp from miles away, while you're moving faster than a speeding bullet. That's the challenge Ohisama faces. It must convert sunlight into microwaves and direct that energy beam with pinpoint accuracy to a receiving station in Suwa, Japan. The initial power output will be small, just about 1 kilowatt, which is enough to run a coffee maker or a microwave oven. But the success of this mission isn't measured in watts, it's measured in the validation of a dream for our energy future. The very idea of space-based solar power, or SBSP, isn't new. It was first imagined back in 1968 by engineer Peter Glaser. The concept is simple in its genius. Here on Earth, our access to solar power is frustratingly intermittent. The sun sets, clouds roll in, and the atmosphere itself filters out a significant portion of its energy. But in the vacuum of space, the sun never sets. It is a constant, unwavering nuclear furnace. A solar panel in orbit could potentially gather 43 times more energy than an identical one on the ground, working 24 hours a day, 7 days a week, unimpeded by weather or night. So, how does this cosmic power plant actually work? It's a three-step process of immense elegance and complexity. First, the satellite must gather the sun's energy. The Ohisama satellite uses a photovoltaic panel, about 2 square meters in size, to capture photons, particles of light that have traveled 93 million miles from the sun. These panels work just like the ones on our roofs, converting sunlight directly into electricity. But this is where the ordinary ends and the extraordinary begins. The next challenge is not just making electricity, but preparing it for a journey through our atmosphere without wires. Once the solar panel generates direct current electricity, the satellite's onboard systems convert it into microwaves. Why microwaves? Because they can travel through Earth's atmosphere, through clouds, rain, and air, with very little energy loss. The satellite acts as a celestial transformer and transmitter, packaging the solar energy into a focused beam. This requires incredibly precise technology to ensure the beam is stable and tightly controlled. The energy that was once diffuse sunlight becomes a concentrated, invisible river of power, ready to be sent down to Earth. The final, and perhaps most critical step is receiving that energy. On the ground in Suwa, Japan, a 600 square meter array of 13 special antennas, called rectennas, waits for the incoming signal. A rectenna, short for rectifying antenna, does the opposite of the satellite. It captures the microwave energy and converts it back into usable electricity. The precision required is staggering. The satellite must target this relatively small array from 400 kilometers up, maintaining a lock with an angular error of less than 1,000th of a degree. It's a cosmic ballet of targeting and transmission. This technology faces immense hurdles, primarily cost and efficiency. Building, launching, and maintaining these systems is incredibly expensive, though costs are falling thanks to companies like SpaceX. Furthermore, every step of the energy conversion process, from sunlight to electricity, to microwaves and back to electricity, involves some energy loss. Early demonstrations have shown efficiencies hover around 10 to 20%. But like all great leaps in science, from the first flight to the first moonwalk, these initial inefficient steps are what pave the way for a revolutionary future. The journey of 1,000 miles, or in this case, 1,000 gigawatts, begins with a single watt. Why would Japan invest so much effort and resources into such an ambitious, futuristic project? The answer lies in its geography and its history. Japan is a nation of islands, rich in culture and innovation, but poor in natural resources. It depends on imports for over 90% of its energy needs, a vulnerability that leaves its economy susceptible to global market fluctuations and geopolitical instability. This decades-long quest for energy independence has driven Japan to explore every possible avenue, from the depths of the ocean to now, the vacuum of space. It's a matter of national security and economic survival. The urgency of this quest was amplified tragically in 2011. The Fukushima nuclear disaster was a wake-up call, shaking the nation's confidence in nuclear power and accelerating the search for safer, more reliable alternatives. While Japan has embraced terrestrial solar and wind power, it faces another fundamental limitation: a lack of space. As a densely populated mountainous country, there simply isn't enough flat, open land to build the massive solar and wind farms required to power its 100 to 25 million people. The sun-drenched, limitless expanse of space offers a solution that neatly sidesteps this terrestrial constraint. This is where space-based solar power's unique advantages shine brightest. Unlike ground-based solar farms that go dark every night and are at the mercy of cloudy skies, an orbital power station would have a near-constant view of the sun. This provides a continuous baseload power source, something intermittent renewables like wind and ground solar struggle to achieve without massive battery storage. The energy is always on, ready to be beamed down to wherever it's needed. It's the difference between waiting for the rain to fill your bucket and having a tap connected directly to an endless reservoir. Of course, the path forward is fraught with challenges. Skeptics point to the monumental cost. A 2024 NASA estimate suggested electricity from space could cost over 10 times more than power from ground-based renewables. There are also public safety concerns, though research indicates the low-intensity microwave beams would be safe for people, animals, and aircraft. But Japan sees this as a long-term investment. The nation has officially included SBSP in its national space policy, with an audacious goal to have a 1-gigawatt commercial station, enough to power hundreds of thousands of homes, in orbit by the 2050s. Japan is not alone in this cosmic pursuit. A new space race is quietly heating up, but this time, the prize isn't national pride or a flag on the moon. It's the key to our planet's clean energy future. The United States, China, and Europe are all developing their own space-based solar power technologies, each contributing crucial pieces to the puzzle. This global competition is accelerating innovation, driving down costs, and turning what was once a theoretical concept into an achievable engineering project. We are witnessing a collective human effort to reach for the stars for our energy. In the United States, multiple efforts are underway. Caltech's space solar power demonstrator MAPLE successfully transmitted power in space and detected it on the ground in 2023, a landmark achievement. Meanwhile, military research arms like DARPA and the Naval Research Lab are also making strides. DARPA's power program recently beamed significant power using lasers, an alternative to microwaves, while the Air Force's Arachne project aims to test key components for an operational system. These projects, though often framed for military applications, are developing the core technologies needed for civilian power grids. China has also declared its ambition to become a leader in this field, with plans for its own trial SBSP satellite in the late 2020s, aiming for a gigawatt-level system by 2050. The European Space Agency is also studying the feasibility of a massive orbital power station, envisioning a future where Europe can draw clean energy directly from space. This international interest is a powerful indicator that the world is taking this idea seriously. The convergence of lower launch costs, thanks to reusable rockets, and advances in lightweight, efficient solar cells is making the economics of SBSP more plausible than ever before. Ultimately, the quest for space-based solar power represents a profound shift in how we think about energy and our place in the universe. It is a vision of a future where our energy supply is no longer tied to finite resources buried in the Earth's crust, but is drawn from the clean, inexhaustible power of our parent star. It's a system that could one day deliver power to remote disaster zones, developing nations or anywhere on the planet, untethered from physical grids. Projects like Japan's Ohisama are the first tentative steps on a long journey, but they are steps toward a future of true energy abundance for all humankind.